it's possible that I might forget again. So in the future, if I just go ahead and start talking, and there's no indication that I started recording, then feel free to give a reminder. It won't bother me. It will bother me if I forget again. There's no recording at all. So, all right. Okay. So, today, I'm going to continue where it left off from where I left off on Monday and finish the coverage of the sequences. I expected there will be time at the end for any questions anyone has. There was the section I'm writing on the board that I'll do each time is section from my notes, the big document that I have in Canvas. All right. Now, what I covered at the end of last time was some examples of determining whether a given sequence converges, and if it does converge, actually finding the limit. And we're going to see some more examples of that now. So that's what we're preoccupied today. How can we tell if a sequence converges? And I use the capital L to refer to the limits of a sequence that does converge. These are the questions we're preoccupied with today. So, first example, find in terms of my sequence, the n to be n squared over e to the n, so an exponential function. Now, did anyone suggest a way to figure out what the limit of the sequence might be if it has one?
Plug and chug.
Well, when you're going to infinity, plug and chug is a little harder as opposed to taking a limit as the approach of finite value. So when you say plug and chug, what does that mean in this case?
Do like 1 and then do like maybe 1,000. See the difference. Or maybe just do successive terms and see the difference between the terms.
That can be helpful to give you an idea of what the limit is. But as far as really showing it, what? This one is if you consider top and bottom separately, then the top is going to infinity n squared, and then e to the n is also going to infinity and goes to infinity. When is infinity over infinity?
So I think should use the L'Hopital's rule.
That's where I was going. So, or and I assume yeah. Okay, so we can certainly. So this is infinity over infinity, one of several indeterminate forms. And so that is suitable for L'Hopital's rule. That says that the limit of n squared over e to the n is the same as the limit of what? By applying L'Hopital's rule to this. Yeah, so yes, so we have 2n here, and then e to the n here, okay. So if we look at 2n over e to the n, yeah, do it again, we get still infinity over infinity. All right. So now we're at 2 over e to the n. Yeah, and so now we can't apply L'Hopital's rule anymore, but we don't need to. We have enough information to see what the limit's going to be. The numerator is constant. The denominator is going off to infinity. So from this, we can conclude the limit is 0. Trying to figure out limits simply by plugging in values. You have to be careful about that because sometimes it can give an unreliable result. So certain techniques that we've seen, depending on the example, L'Hopital's rule, or for instance, the example I had is a difference of square roots, multiply and divide by the conjugate, or if it's a fraction, you're multiplying and dividing by the highest power of your variable. These are reliable techniques to determine what the limit is. Okay. Question about this one. I'm going to give another example that suggests the use of L'Hopital's rule. It's actually my favorite L'Hopital's rule example. N over square root of n squared plus 1. Now there are there's more than one way to figure out the limit of this. Some of you may realize what the limit is already. But the focus here in this example is what happens if you use L'Hopital's rule. So this is an infinity over infinity situation, so you can use it. So if you do, okay, so you get 1 up top. And then what happens when you take a derivative of a bottom? What do you get? Sorry, what?
Can be just, I don't know what's it called.
Yes.
Square root of n squared plus 1 over 2n.
Okay.
N squared over square root of n.
Yeah,
Square.
I'll make sure that we're not covering several steps at once, because just focusing on the derivative of this.
Oh,
Yeah, let's go one step at a time so everybody can see.
Isn't it first 1/2?
Yeah,
Okay,
and then as I mentioned, we carry it up.
this is where I'm getting confused, yeah, but okay.
So minus 1/2, and then what happens?
Times 2n.
Times 2n by what rule?
Powers.
Well, more specifically, because yes, also there's a general power rule. Yeah, yeah, we were using a power rule here, but because we have not this n in here, that's a chain rule. Okay. All right. So that's what we have driven to the bottom. But now to see what we're dealing with here, we'll cancel the 2's. And now what's going to happen is we have reciprocal of what we started with, because the n squared plus 1 to the minus 1/2, we move that up top. So now it's n squared plus 1 to the plus 1/2. And this n is still sitting down here. All L'Hopital's rule did was flip the fraction.
yeah.
And you can imagine what would happen if, because we're still in an infinity over infinity situation, what would happen if we did this again? You flip it again, so you're in L'Hopital's rule nightmare, Groundhog Day. So what would be?
Oh, okay. Oh, okay, I see.
Yes. So what should we do differently? There's more than one right answer. That would give us the limit.
Could you not just distribute it to the end?
Well, okay, and
In
you
the,
mean something like this?
Yeah.
Yeah, yes. So so instead of using L'Hopital's rule, we perform some algebraic manipulation, and that will give us the limits. So now you have 1 plus 1 over n squared, and there it's easier to see that the limit's going to be 1. Because that's going to go to 0, and this is all we're left with. So,
Okay, you,
Yeah, because it's square root and square over, yeah.
yeah, so by making it into 1 square root. Get that, yeah.
How did the square root end up on the bottom?
How'd
How'd you go?
Because you squared.
Oh, from here to here?
Yeah.
Okay, so here we have n squared plus 1 to the minus 1/2 in the denominator. That's the same as n squared plus 1 to the plus 1/2 in the numerator.
No, you're right. Okay, and then how'd you get one more over there?
Okay, how to get,
To that, yeah.
oh, I just rewrote n as square root of n squared.
Okay.
Which is okay in this case because n is positive.
Okay.
Because really this is absolute value then, but, okay, so. Other questions about what's here? Another way to work out this problem, considering that the whole fraction is positive, what? Okay, all right, what you could do is square this. And now you have n squared over n squared plus 1. Figure out the limit of that. And it's easier to see that that's going to be 1. And then take a square root of a result. And you get 1 that way, and the reason why that's okay in this case is because we can see the whole expression is positive. So we don't have to worry about getting the wrong sign or anything like that. But I actually did that with this example way back in, I think it was 2003 when I was teaching in Cal 2 at University of California, Irvine. Okay, you can square it, take the limit, take the square root. And one student got really, really mad at me. It's like, you can't do that. And it's like, dude, it's a calculus class. So just, okay. But gonna have passionate students, but don't forgive a pun, there's always a limit. Okay. All right, so certainly L'Hopital's rule in a number of cases can be helpful for getting. Okay. Now let's look at a particular kind of sequence that's going to come up now and then. Gives us another way of determining where there's a limit. Called an alternating sequence. So what is an alternating sequence? So an and an plus 1 have opposite signs. All right, so you have positive, negative, positive, negative, positive, negative, so all the way through a sequence off to infinity. Okay. Now, so that means it's possible to write the terms of the sequence an as -1 to the n times some expression bn, where all of these have the same sign.
The D in?
What?
I'm sorry, what?
bn.
Oh,
Yeah. Okay. So the one easy way to see if such a sequence converges, I'm going to show you through an example. I'm going to find my sequence an to be -1 to the n over n plus 1. So what does my sequence look like? So A1 would turn out to be minus 1/2. A2 would be plus 1/3, minus 1/4, plus 1/5, so on. So I'll then consider sequence Bn defined by taking the absolute value. So Bn, we just remove a sign flipping part. That's just 1/n plus 1. Okay. Now, the limit of sequence Bn is easy to determine. What would it be? This is 1/n plus 1. Yeah, it's going to be 0. And from that, we can conclude the limit of the original sequence An is also 0.
Oh, okay.
So in general, we have an alternating sequence, but you look at just the magnitudes. If the magnitudes are going to 0, then the original alternating sequence is also going to 0. And this will help us later when we look at alternating series. We have some alternating sequence, and then we're summing up all the terms. The fact that it's alternating, we can figure out whether that's going to converge or not relatively easily. All right. Now, the earlier example, n squared over e to the n. The numerator denominator featured very different types of functions. The numerator was a polynomial n squared. The bottom was an exponential function e to the n. Sometimes we can easily figure out what's happening in a sequence based on understanding which types of functions grow faster than others. So what I'm going to do is give you a hierarchy. I'm going to list categories of functions in order of growth rate. The slowest to fastest. Okay. Oh, I just realized in the notes I have fastest to slowest, but hold on. All right. So a very slow growing type of function is the logarithmic function. So any family of logarithmic functions, like ln of n, or log to the base 10 of n, things like that. So as n goes to infinity, the logarithmic function goes to infinity, but much more slowly than other functions. Next category is polynomial functions, basically n to the p, where p is a non-negative integer. So n squared, n cubed, n to the fifth, n to the 1,000th, all fit into this polynomial category. Next, exponential functions. So 2 to the n, e to the n, b to the n, where b is greater than 1. If b is less than 1, then that's not exponential growth, it's exponential decay.
So that's for logarithmic, that's ln of n and then log n.
Log to base 10 of
Oh,
n. Yeah, the common logarithm function. And finally, factorial.
Um. Log B minus n,
Right. Okay.
or
Like log subscript 10 of, yeah,
n,
of n. Yeah. So the idea is any function in one of these categories grows faster than any function in the category above it. So it doesn't matter if I have, say, n to the 1 million. That's still going to grow less rapidly than any exponential function, even if the base is only slightly greater than 1. The exponential function will eventually still win out. So what does this mean in terms of determining limits of sequences involving these kinds of functions, particularly if they're in a fraction? So if an is a fraction where we have a slower growing function or a faster growing function, doesn't matter what kind. Just that this is from a slower growing category, this is from a more rapidly growing category, then the limit of the sequence will have to be 0. So you can just conclude that immediately. If I put something like this on a test, for example, like the example we saw earlier, n squared over e to the n, you can just indicate, by growth rates, the limit is 0. You wouldn't have to do any other work. Similarly, if I have faster growth over slower growth, like a factorial divided by n cubed, that's going to go to infinity. So or minus infinity, depending on whether the expression is positive or negative. So in other words, faster growth over slower growth, that sequence is going to diverge. It's a way to quickly determine in certain cases whether sequence converges or not. Questions about growth rate?
I just want to make sure that if it's slower is faster, it will converge, right?
Yes, yes, to 0. Now, if you have functions in the same growth category, it wasn't intentional, but still. It could be fairly easy in those cases. Like, for instance, if it's a polynomial, if you have lower degree over higher degree, it's going to go to 0. Higher degree over low degree is going to go to infinity. Same degree, you look at the leading terms, for coefficients of the leading terms, and that's what limit. Exponential, you look at the bases. Larger base over smaller base is going to go to infinity, or plus or minus infinity. Smaller over larger is going to go to 0, and so on. Okay. And actually focusing on the exponential category in particular, that leads to what are called geometric sequences. I've seen a little bit already. It's very important when it comes to theories. Well, in this case, your sequence is defined as some number r raised to the nth power gives you your nth term. So how this sequence behaves depends on the value of r. So if the absolute value of r is strictly less than 1, then the sequence converges to 0. If it's greater than 1, sequence diverges. I'm not saying what the limit is, just because it depends. If r is larger and positive, it will go to plus infinity. If it's negative, but absolute value greater than 1, for example, -2, it doesn't even have any kind of, even an infinite limit, because it's going to go back and forth between positive and negative values. So it's totally all over the place. The point is, it still diverges. If r is equal to 1, then every element of the sequence is 1. So the limit is 1. Now, what's the one case I've not covered?
Yeah.
That's under absolute value of r is less than 1. That'll be covered under absolute value of r greater than 1. It's one single solitary number that's not covered. No, it's still a real number.
0, 0.
That already came up. That falls under this case. It's certainly.
I don't know what it could be. Okay, if it's between 0 and 1.
That's not covered under this.
I don't know, man.
-1. Notice here I had no absolute value.
What?
Yeah. So if r is equal to -1, yeah, because here I had absolute values greater than or less than. Here I only had r itself equal to 1. R equal to -1, then you're just going to go back and forth between -1 and 1. So it diverges in that case. It's going to keep bouncing back and forth between those two values. Actually, it's worth mentioning that since someone asked what it's complex. If R was complex, we're not really going to get complex numbers in this class because yikes. But these two would still apply. You'd have to use the appropriate definition of modulus or absolute value of a complex number. And if the absolute value of a complex number is equal to 1, but the number itself is not equal to 1, then it falls under this category. It's still going to diverge. It's never going to settle on a particular value. All right. Some questions about these kinds of sequences. Now, last time, actually both classes, previous classes, I talked about recursively defined sequences. So each term is defined in terms of a previous term. So how would you compute the limit of something like that? Turns out there is a relatively simple way to do so. Um, um, I'll illustrate by way of an example, and I'll give you a general principle. So this is a recursive sequence actually brought up last time, and then from Newton's method. But an plus 1 is defined in terms of an.
With an over 2 plus 1 over an.
Yes. So does the sequence conversion? If so, what is the limit? Now we're going to simplify matters by assuming that we somehow know at least a series, the sequence converges, and then from there we're going to get the limit. Sometimes a sequence like this might not converge. So the main idea, if the sequence converges to some limit that I'll call L, and right now we don't know what L is, not yet. Then the limit of a slightly modified sequence an plus 1. So if I have a sequence A1, A2, A3, and so forth, I define a new sequence that starts with A2, A3, A4. That's going to have a safe limit. So because n is going to infinity, in the end, you're still talking about the same terms. You're just starting at a different point. So what?
When n tends to infinity, n plus 1 upon an is equals to 1. Can we do that? For different sequences.
Yeah.
Right, so we got the limits. The limit n tends to infinity, an plus 1 over an is equals to 1. Can we see this?
Oh, not necessarily. Yeah. Well, because that depends on the sequence. Yeah. Well, but besides, well, okay, if a limit is non-zero, then that claim is true. It still doesn't tell us what the limit is. Yeah. Okay. So what you can do is take the limit of both sides. Now, the limit of the left side, that's just going to be L. Now we don't know what L is, but whatever L is, that's going to be the limit.
Wait, what is that? Like after the equal sign there at the very beginning, no, the other
Oh,
one.
this is this implication.
Oh, okay.
Now, the limit of left side is L, right here. And then the limit of the right side will be L over 2 plus 1 over L, because L is the limit of AN. So by limit laws that you learn in Cal 1, the limit of this whole expression would be this. So now we don't know what L is, but we have an equation that defines it. So now I can multiply both sides by L. And now I can rearrange this, and I get L squared is equal to 2. So that would tell us that the limit is plus or minus the square root of 2. And which one it is, actually, it's going to depend on how the sequence starts out. Because suppose your first term, A1, suppose it's positive, then this whole expression is going to be positive. As long as AN is positive, AN plus 1 is going to be positive. This sequence, this particular sequence, it's just this example, will never change sign. Similarly, if I start out A1 being negative, every term is going to be negative. So that's what will happen is if AN equals 1, the limit will be plus positive square root of 2. Otherwise, it'll be negative square root of 2. I better not choose 0 because it'll be undefined.
Okay, I'm confused pretty much since the arrow there.
Here,
Yep,
all I did was take the limit of both sides of this equation
okay,
as n goes to infinity. So carbon copy from here to here, just taking a limit.
okay.
Because if these two expressions are equal, then their limits must be equal.
Okay. So
Now-
like, how do you get the L over 2 plus 1 over L? Then you get-
Limit laws, the limit of this is soon to be L. So the limit of this would be L over 2. Same thing here, the limit of AN is L, the limit of 1 over AN would be 1 over L. So those are all the limit
Okay,
laws.
okay,
So that's how I get this expression from here.
okay,
Whatever limit you have for AN, you just plug that in.
okay,
But these two have to be equal, therefore these must be equal.
okay.
And from here, it's just algebra to get from this equation to this one.
How do you get to the L squared?
I multiplied both sides of this by L. To get from here to here.
Okay, and then how do you get
And
L?
then, and then I move this. I move this term to the other side, and then multiply both sides by 2.
Oh. Okay, L squared, so then you squared that, but then that's.
Yeah.
It'd be L to the -1 and L to the. L to the -1 plus. Wait, how did? Okay, if you have 1 over L, that would basically be the same thing as L to -1, correct?
Yeah, so multiply by L. 1 over L times L.
Oh, you're just multiplying by 1 L. Okay, I was thinking you're multiplying this. Okay.
Okay,
Okay, now, now I see where.
okay. All right. So when you have a recursively defined sequence, what you can do is make the assumption that there is a limit. And then keep in mind that if the index shifts, that's still going to have the same limit. So you arrive at an equation like this, and this equation you can solve for the value of your limit. Now, keep in mind, we're making the assumption that the sequence even converges. It will not be difficult for me to write down an example of sequence like this that doesn't converge. So you have to be careful about that. But if you, it's really give you a good idea to see what are terms of a sequence look like. For example, if I here, this solving this equation doesn't tell me positive or negative, but by knowing what the first 3 terms are, saying, oh, it's positive, then the limit's going to be, I know the limit's going to be plus the square root of 2. Right. So, but this property right here gives us a way to find the limit of a recursively defined sequence. Questions about what was done here?
Okay, at first, how do you get L squared equals 2? Yeah, I'm confused about that part.
That's from working with this.
Yeah.
All right, it's just algebra at this point.
Okay.
Yeah, so, write this down. I can't cover every single algebraic step in this class. And that's what you'll arrive at. Okay,
You should start erasing from the other side, please.
what?
I'm writing on the last row. Can you start erasing from the other side?
Yeah, I wasn't going to erase this
I'm
anyway.
sorry.
Okay. Yeah, I'm always gonna alternate. So, but that's fine. If you need more time to write, you can always ask, but.
How later today I'm gonna post this video,
Why?
because I just kind of want to review.
I mean,
Or do you think like you'll get to it like the next day? I'm just wondering.
okay. No, that's not, sorry. I'm just curious as to why you're asking. I'm just,
I just want to review it, so.
okay. No, I'm, okay. I generally always try to post each class day's video before I leave for the day.
Okay.
So maybe this
Thank
evening, so, yeah, okay. Reason I'm asking is if there's something you're confused about, you know, we could take time to address it now.
No, it was previous, and I forgot about it, so I just want to make sure I'll be able to go.
Okay.
In the video. I'm
Okay.
sorry.
I feel like you guys are trying to walking on eggshells around me, and there's really no need to. Right. So I'm not sure where you're getting his vibe from me.
I'll be honest with you, I don't understand the algebra either. For the L squared equals L squared over T plus one. I'm sorry, but. Okay.
Okay. Do we have any other questions about this?
Well, can you do another example of this, if you don't mind? Could we do another example of recursive defined sequence?
Okay. Actually, I was going to do an example of one that I know the sequence happens to diverge. We can see what the fishbowl is. Okay, so each term, actually, you should write it this way. Because you get each term by doubling the previous one. As before. With limit of an equal L. That means the limit of an plus 1 is also L. So from that, I take a limit of both sides. Then the left side will be L. And then we would have 2L that way. Now, if L equals 0, certainly this will be satisfied. But actually, yeah. Yeah, that's the only way that it can be satisfied is if L equals 0.
Because otherwise you'd say 1 equals 2.
Yeah. Now, if the first term of the sequence, A1, happens to be 0, then yes, everything I wrote here is valid. But if A1 is equal to anything else, any non-zero value, this sequence would actually diverge. So that's why I mentioned you have to be careful. We're making an assumption that the sequence even converges in the first place. If it doesn't, then let's see, but this approach could go badly. Or give you a wrong indication.
So when does it not diverge?
If the first term is 0. Okay. I'm trying to strike a balance between covering what I'm required to cover and making sure all the questions are answered. I get feeling that you'll need to apologize for asking a question, and that is absolutely wrong. It is literally my job to answer questions. But again, I have to strike this balance. If a question cannot be addressed during class time, then you can talk to me after class or outside of class or later. Questions will be answered. But again, I'm having to juggle the two things. So I'm just asking you that you keep that in mind. And if you have a question, it's your responsibility to ask it. And I do want those questions to be asked because I want them answered. Okay. All right. I want to make up another example. But it's not the easiest thing to do on the fly. Let's see.
Okay, hold on, where would the on this one, where would the +1 go and then, okay. Where did the a n +1, where did that go?
Well,
A n,
from what I stated earlier, if a limit of an is L, the limit of an plus 1 is also L. But if you have the same limit, so that's why I would write L down here. So +1 didn't actually go anywhere.
It's saying that AN plus 1 equals L.
Yeah, so. That,
okay, so is it that just saying the next iteration might also just be,
yeah, but the thing is, we're really talking about the same, as we go into infinity, talking about the same terms, so we have to have the same limit. The only difference between this sequence and this one is that you think of this as of a first term, very first term is omitted. But that has nothing to do with the limit. The limit's what happens as the index goes to infinity. So the sequences may not start out the same way, but they'll end the same way.
okay, then how did it, okay, then, and first L equals 0, you have L equals 2L.
It's the only possible way you could. The only possible way L could equal 2L is that if L equals 0.
Oh, okay,
Yeah, just by moving to the other side.
gotcha.
Okay, that's the only way that out. Let's see. Using MATLAB to help me.
You don't hurt your computer, getting all the chalk in there.
Oh, well, I've survived for a couple years now, but okay. Okay. I think this might work. We'll find out. Okay, so my sequence. So this is a case where each term of the sequence depends on the previous two. Kind of like Fibonacci numbers does, it's only with different coefficients. Oh, actually, these should be plus. So let's see what happens in this case, where if an has a certain limit L, then an minus one has a limit L, and plus one has a limit L. They all have the same limit. This isn't gonna go well. Is it? Although, in fact, actually, this. Okay. What's the only possible?
0.
Yeah. All right, so now what I'm going to do is, I need to pick, if I want to see what the sequence looks like, I'm going to pick, I need to pick 2 initial values to kick it off. Just like if Fibonacci case, we needed 2 numbers. So choose A1 to be equal to 1, A2 being equal to 2. So then if I have 1.5 and 5/4. Yes. Okay. I think this is also going to diverge. Yeah, it is. Okay. Yeah, it is. I started plugging in values between A3, A4, A5, the numbers start growing. So, okay. It's not the kind of problem where I could just make up an example on the fly. But if I can outside of class, then I can add it to that. Okay. Another way to tell sequence conversions in this category that are bounded and monotonic. Now I'm just explaining what those terms mean. Okay. So sequence is bounded if we have a following that all the terms in sequence in absolute value are less or equal to some constant m. For example, if an is equal to -1 to the n, that is bounded. In this case, we can choose m equals 1. As long as we can find some m that works, then that would be a bounded sequence. But if I choose an equal n squared, that is unbounded. Because the numbers will just keep getting larger and larger off to infinity. That's one term. The other term. When is a sequence monotonic? Yes. Both terms are going in one direction. So in this case, the terms are, in this case, non-decreasing anyway. Or goes the other way. this is an example of, this one means to be non-decreasing. Or increasing. If I had strictly less than, that would be an increasing sequence. If it was strictly greater than here, that would be a decreasing sequence. As long as it's one of these two, then we say the sequence is monotonic or monotone, either one. Okay. Another way of putting it. No oscillations allowed. Can't go bouncing back and forth. So in fact, n squared is an example of a monotonic sequence because it's steadily growing. This one minus 1 to the n is not monotonic because it keeps bouncing back and forth between two values.
So technically, if it's like a wave.
Yeah. So that may be bounded if a wave has a limited amplitude, but definitely not monotonic.
Side.
What?
Yeah, sine, cosine.
Yes. Yeah, so yes, sine and cosine are bounded and not monotonic. So if a sequence and is bounded and monotonic, it converges. Now, because when a sequence diverges, what kind of behavior it could exhibit? It could go off to infinity or minus infinity. Well, it can't do that if it's bounded. Or it might be bouncing back and forth between different values. But it can't do that if it's monotonic. So as long as both conditions apply, we know the sequence converges. Now, the sequence doesn't have to behave these two ways to converge, but if it does, then it will. So these, you can think of these as sufficient conditions for convergence, but not necessary. Yes.
Okay, what's those word? What do those words say up there?
Non-decreasing, non-increasing.
Why not just increasing?
Because I have less than or equal to.
Okay.
I mentioned that earlier.
Oh, okay.
Yeah.
You mentioned that sine wave is not
It
monotonic.
is not monotonic. It is bounded.
Yeah.
Yeah. And sure enough, that sequence based on elements of a, like if you pick out certain points on a sine wave, usually will diverge. I say usually because, for instance, if I have a sine wave, suppose I pick an to be sine n pi. Well, sine n pi is always 0. So that kind of trivial sequence would converge, but
It's like an audio wave, it's like a mono wave, it's just one
Yeah.
channel, and then
Yeah.
stereos too.
Yeah.
You kind of look at it that way.
yeah. So, whereas if I took sine, if I let an equal sine n, suppose sine of any integer, that's not going to be any like the nice angles. It's not going to, they're not going to be cyclic. That sequence is going to diverge because it's going to go back and forth between so many values between -1 and 1.
So does that say in parentheses, no?
No oscillations.
Okay.
Sorry, my penmanship is not the best. That's why I type up my notes too. To eliminate any doubt about what is written here. Okay. Okay. I have a couple of examples. These kinds of sequences. I let an be
That negative.
Yeah, minus n. All right. Now, if you look at visual terms, so if I let n equal 0, you're gonna get 1 minus 1, that would be 0. A 1 is gonna be equal to 1 minus a half, so 1/2. A 2 is gonna be 1 minus 1/4. And so on. If you were to keep computing terms, you would find that you're never going to get a number that's greater than 1, which makes sense because this number
It's getting smaller.
getting smaller and smaller.
When you're starting at 1.
Yeah, and even then, you're taking 1 and you're subtracting something that's positive. So you're never going to get something greater than 1. We also see we're never going to get anything negative because we started off at 0 and then
The base number is a 1. And or the constant's a 1, so.
Yeah. So this sequence is bounded. And happens to be strictly increasing. Now, this part, a good way to confirm, if you're not sure, for whatever example you have, examine this difference, an plus 1 minus an. If that difference is always positive, then your sequence is increasing. If it's always negative, then it's decreasing. So in this case, an plus 1 minus an would be 1 minus 2 to the minus n plus 1 minus 1 minus 2 to the n. The ones will cancel out. So you're left with 2 to the minus n minus 2 to the minus, oh, there should be parentheses, plus 1. What I can do here is I can factor out 2 to the minus n from here, and I'll get 1 minus 1/2. So in the end, it simplifies. The difference between two consecutive terms simplifies to this, which the key thing here is that it's always positive. So because the difference between two terms can be seen to be always positive, we know that the sequence is increasing. The questions about how these steps play out. Because it is bounded and increasing, we can conclude right away that it converges. Now, that doesn't say anything about what the limit is. We still have to figure that out. What would it be in this case?
So basically, you're saying that it's greater than 0?
Yes. Yeah, because it's 2 raised to a power, it has to be positive. What would the limit be in this case? Yes, because what's being subtracted from 1 is going to 0. Yeah. Questions about this one? One more. And n plus 1 over n plus 2. now, there's a way to show that it's increasing, but what I have here in my notes show that it's increasing. Probably not the easiest way to do it. You can read that in my notes, but I'll show you an easier way. Because if I try to force the numerator match the denominator, I want an n plus 2. All right, fine. I'll put in a plus 2, as long as I also subtract a 2. Then I can separate this into 2 fractions.
Your notes are this, so you think it's easier.
This is what I think is easier.
Oh,
So now I get 1 minus 1 over n plus 2. So if we use this formula for the terms of a sequence, then it's easier to see that the sequence is in fact increasing. Why? Because what you're subtracting off from 1 is getting smaller and smaller. You can also do what I just did here for a previous example. Let's go ahead and look at this difference. And by working it out correctly, you can see that the difference is always going to be positive. So again, you can see the sequences increasing. Okay. Any questions about this one? Or homework problems, because I've come to the end of what I want to cover in the notes, and there's 7 minutes left.
So are this is the end of this unit, our homework's gonna be due a week from today or 2 weeks?
So the
1 week from today is homework 1 on sequences.
oh.
Are we still allowed to ask questions about sequencing while we're going over? I'm assuming series is what we're gonna be covering next week.
Yeah, okay. So my thinking is that I finished covering a section. Okay, now you got to, only then is it safe to really start the whole homework. So then during the following class period, I may have started covering the next topic, but then whatever time is left at the end, can be used to ask questions on that assignment.
Okay.
So hopefully help you finish it by the end of the next class day.
Okay, so wait, when's the assignment due?
1 week from today. So again, I'm finishing sequences today. That starts the clock of 1 week. I'm not really big on, someone allowed to do this, just ask. And I'll do my best to answer. So as it was quite early in the semester, so I actually held my first Wednesday morning office hour. And not many people, I guess a lot of people working on the pre-test, so that's good because even though it doesn't count, it can be good to see where you're at. And I'll be holding my next office hour at the end of today at 5:30 to 6:45. The times you can see on my door. So if there's any difficulties, then it's incumbent upon you to do what it takes to address them, and if that means asking me, then that's what you should do. All right. Yes.
And then for like the pre-test, how similar would you say that is to like the actual test questions? I mean, that's like a good portion of the review, or what are the notes better?
Okay, I haven't looked very closely at the pre-test questions. The best approximation I can give you of a real test is a practice test I'm going to put out.
Okay.
but it should be at least a good starting point to see what sort of things you should be able to do. Actually, yeah, admittedly, I should have looked at the pretest. I also didn't expect that many of y'all to do it. Because it doesn't count for a grade.
I gave
I
up.
don't know, it was like a rush or refreshing.
Yeah.
Okay.
Now, I've not yet posted a quiz for this module because we're still a ways to go within the module. And before I do, I'm gonna look at it because these are things that I inherited. And I want to make sure, like, if it's something that I would never ask and I need to delete it. Yeah, so I'll be making sure to screen these things before I put them out, even the ones that don't count.
Okay.
Okay. Right. The last 3 minutes, anything? Yes.
Okay, so just get back, how did you go from n+1 over n+2 to the next one?
Oh, from here to here?
No, before that.
Oh, from here to here?
Yeah.
Okay. I want, since the denominator is n+2, I want an n+2 in the numerator. Let's go ahead and put a 2 there. As long as I compensate for it by subtracting it. Yeah, so it's an add subtract trick.
Okay.
Yeah, and this is something I do often. If I want something to be in my expression, I'll just go ahead and put it there, as long as I perform the corresponding inverse operation. So I'm not changing what I have, but that's how I can get it into the form that I want. Yes, but it's that kind of thing. Yeah, because that's basically an add subtract trick. It's guys. Actually, I once saw a teacher present it that way. That like if just completing a square is like, here's your magic number to, yeah. So it's not kind of touch passing to be, but anyway. Okay. All right, well, I mean, I'm done. So oh, no, that's in class. On paper.
Okay. That's not there. I'm very not heavy interest in online, so in my early accommodations. That's just been where it is the online program isn't working for me, if I can do the on paper. If the homework gets to me, I'll tell you, but it wasn't last semester.
I remember seeing that in your, probably, that I say up about that, I wasn't sure what was meant by that, and they never answered me. But that,
So I don't.
oh,
think we'll-
okay.
Yeah, so.
But yeah.
Like 99 Friday.
Okay. Well, what I can easily do is just, save you some of the PDF, print it out, and that's, then you work it out on paper, so, I mean, that's, and I'll grade it, so that's.
It shouldn't be an issue, it wasn't
Okay.
last
Okay,
semester.
and so far it seems to be okay. So,
And I had something like that in high school too, it wasn't an issue.
Yeah.
If it gets to, and I'll tell you that.
yeah, okay.
Is there a second?
No, I don't have that.
And shoot the lecture notes that you posted and the PDF of the
Hold on,
book.
it's being recorded.
Yeah.